Okay, hey everybody. We're going to do a recording on how to do Euler's method. It's rather challenge because you got to make sure that you're punching the right buttons on your calculator if you go old school. I don't know how I'm going to test it. I'm going to see you fill in a table and stuff like that in such a way that there's a lot of software online that you can use, and it's not like that's not the thing. I want you to understand and appreciate how this can be done and how mathematically it makes sense, but also appreciate what they did back in the day pre-computer assistance. Okay, so what we have is a formula for Euler's method, and to kind of remind you, you've got a curve maybe that's cruising through space, and then you've got a point on it, let's say this color. You got a point on it maybe here, and that's your initial condition, okay? That will be, if you start building a table, you go, well, I've got x0 and I've got y0, and you know, there you go. And I'm going to look for x1. I'm going to let x1, x2 just go up by the same amount, okay? So you have something called a step size here. Right there, they say use the step size of 0.1. So x1 would be x0 plus 0.1. But it's the y0 that's interesting, because what you do, if you superimpose this and say that this is x0 on the x-axis, then you go over a ways, maybe make it ridiculous and go, this distance I'm going to go over h. Euler's story was, I don't know what the function is, but I'm telling you, I can take its derivative and I can walk up its derivative to where I'm here. And Euler's going, I'm thrilled that I'm kind of close to the actual function's curve, okay? So you end up, and I know we talked about this once, but we end up with a formula that says, you know, yn plus 1, the very next one is, that's an n, yeah, is equal to yn plus your step size times your slope there, which is given by your function. And let me finish this. I'll go x n comma y n, and I'm going to say that y prime is equal to that function. Okay, so that's what you see a lot in our textbook. Is it's a multivariable function, and there it is, and you just plug into this thing. So here's our problem. Okay, and you're supposed to take this information and run with it. Oh boy. So you start with the table and you go, okay, so I'm going to call this x sub n. So like this might be n is 0. So I look at the initial condition. That's where we start. The x is 0, the y is 2. So x0, I'll write it out. x0 is equal to 0. And if I go y sub n over here, then y0 is equal to 2. And we're off to the races, as they say. Okay. Now the next one, you respect the step size. So x1 goes up by 0.1. Depending on where x0 is, you tack on the h. So now x1, we're at 0.1. Okay, this is where the fun begins. Now we use the formula. So we're going to say y1 is equal to y0 plus hf of x0 y0, which is elaborate, but really you start getting your hands dirty. You start going, okay, I'll put it over here. Y0 is 2, plus your step size is 0.1. And now we respect the derivative formula. That's your f of xy. It turns out in this problem, it's minus 2 times x times y. The slope is always that, no matter what point you're at. So you do that. You just go times minus 2 times x. Now, which x is it? The previous point. It's the slope. Notice the picture. It's the slope at the previous point. Well, the previous point was 0, 2. So this guy says it's the product of minus 2 and the two numbers. So you get a 0 and you get a 2. And all told, what you get is that y1 is equal to 2. So we have 2 and we have 2 again. We have this point, 0, 2. Now we have 0.1 and 2. And you go again. And I'm going to stop. I'm going to show you the table I filled by going over this process again and again. So the next guy would be, let's say x2 is bump it up again. This guy just keeps on going point by 0.1. So that's that guy. If you go to x3 and you have to, 0.3. Now, I should have said this at the beginning. What are we trying to approximate? We're supposed to approximate the function at 0.5. If we keep bumping up by 0.1, we're going to get there in a couple more steps, aren't we? If we get past that, yeah, you'd go x sub 4 is 0.4, x sub 5 is 0.5, and then you're going to stop. The x's are, you know, pretty easy, but it's the y values that you have to work on. So here we go with y2. y2 is y1, which is still 2, plus the h, which is 0.1, and then times this function, the derivative again, minus 2. This time it changes. It's 0.1, because that's the previous point. And then times 2 again, because that didn't change. And so what we have is that y2 ended up being, I forget, what was y2? It ended up being 1.96. I know it's a little sloppy, and so I was using a big piece of paper and doing a table, especially on the next section, which is coming up in a moment. But you notice what we have, and I like to make a mess. Here's the first point, here's the second point, and here's the third point, and you keep going down the line. If you keep doing this, you should get a table looking something like, well, make your own table, of course, but here's a table. You can see the x is going from 0 to 0.5 because the step size h is 0.1. And as you compute the y's, this is what you get. And you end up at the bottom, when x sub n is 0.5, you can say the function, which I don't know, okay, evaluate at 0.5, my approximation is this guy right there, the last one. In fact, every one of these is an approximation of the function. At what is y of 0.1? Well, it's about 2. What is y of 0.2? Well, it's about 1.96. And in fact, the book, I didn't mention this, or write it down, I should say, they actually, in the homework, they give you the actual solution. And you're supposed to use it. And this one is y of x turns out to be, I think it was 2e to the minus x squared. And so this table here, that part of the table, I just crunched the numbers. And what you're supposed to do is you're supposed to compare these guys. These guys, of course, are perfect because that's, you both start at the same spot. But then you got 2 and 1.98, 1.96 and 1.92, 1.88 and 1.82. And you notice at the bottom that they really start to diverge after a while. So the farther you go, the more cumulative error that you accumulate. So the homework in section 2.4, this is how you're doing it. You're going through this iterative method. I just wanted to point out one more thing here is I ended up using the calculator, this thing, and storing it, A, B, C, D, E, and whatever. I just stored it in A as I went along. And my formula, when I did this, you know, what happens is this A, of course, changes, and this 0.1 doesn't, and this -2 is part of the formula of the derivative, but this guy also changes. So there was no real quick way of doing it. I just kept on having to, you know, type it out again and again and again to get it right. Okay, so that's that one. Now let's go to the improved Euler method, and the improved Euler method has more moving parts. So if you want to pause and practice, note the timeline of the video and then come back and look at it again. I thought I'd just throw them together. So I guess, I don't know. I like it going together. So here it goes. The improved Euler's method, what it does is, well, it's a good improvement. It improves the error by a power of 2. It lessens it, so to speak, you know. So you have a curve again, and you've got your initial condition floating here somewhere. And that's your x0, y0. I always like the geometry of it, you know. And then you've got the number line going like this. And you got, this is x0. And you jump out to h or something like that. So what we do as usual, Euler's teaching us, why don't you use that tangent line? Of course, if you use that tangent line, what they noticed is, you know, when I finally get there, I'm way up here, and the function is actually pretty far off. And of course, you might know that the smaller the step size, the better your approximation also. So this is an effort to kind of step your way towards a close function value. And you can see that that first attempt wasn't so good, but this one is a lot better, as you're going to find out. What they do is they don't stop there. Okay, this slope here, m is equal to f of x0, y0, but then they come along and they go, now let's do the slope at this point, and that'll be m is equal to f of x1. And then they call it not y, but u1. And then they take those slopes and they take their average, okay? So you take the average of these slopes. Wow, whoever thought of this, go, go, go. So when you take the average, you're gonna have a slope that might be a little better and you might have a better approximation. And so this y1 has a formula. y1 is equal to, of course, y0 plus, of course, your step size. And then you take the average of those two slopes. So it would be, in this case, f of x0 comma y0, and then plus f of x1 and u1. And it turns out it's a really good approximator. Okay, so when I did this, I created a big table. And because it gets complicated, it honestly does. You just simply go, well, I know there's an x0. So x0 is 0. And way over here, I'm going to go y0 is equal to 2. And then I know that x1 is equal to 0.1. But I was working on this thing, and I wanted it as accurate as possible. So every little step I kind of saved. So I'm going to show you what I did. It worked finally. I forgot to store something once, and I had start all over again. So it's kind of painful that way. But the next step here would be, I'm going to compute, let's see, the derivative. Okay, so I'm going to use this actually. So I'm going to say the derivative, I don't have a name for it, but I'm just simply going to go minus 2 times 0 times 2. And then I'm going to go, and therefore u1 is equal to y0, which is 2, plus the step size 0.1. And then this guy turned out to be 0, and then times 0, and so u1 is still equal to 2. Remember that happened before? Okay, that's a 2, and this guy's here, and this point goes with that. Then I went for the slope again, and I went minus 2, and I used the next 2 points. So minus 2, whoops, minus 2. We're almost done here, actually. I'll show you the table in a moment. Minus 2, and then 0.1, and then see these 2 points I should highlight. I'm using these 2 points now, okay, and then 2 again. And in that case, you get whatever you get. Let's see what I got. I can't even do it in my head. I think it's a negative 0.4. Yeah, of course it is. It's a negative 0.4, okay? So those guys are interesting. They're important, okay. So I've got, these are slopes. These are the 2 slopes. Those are the 2 I'm going to take the average of. And so therefore, way over here, y1 is equal to y0, which is 2, plus the step size 0.1, and then times what I did instead of divide by 2 is I just multiplied by 0.5. And then I go times, and then I take those 2 slopes, 0 and 0.4, and add them together to take their average. And I got y1 ended up being, and I'm going to cheat and look again, and it's 1.98. So I've got the new point. See how it is there's an intermediary. You got to go slope. You got to do like your Euler method. You find u1 with the Euler method. Then you find the slope of that point, and then you take the average and you compute your formula. Easy. No, I'm just kidding. It's a mess. And then you keep going. So then you go, okay, so x2 is 0.2. All right, maybe it's good to see one more go round and look at the table again. Now I go for the slope, which is, yeah, this, okay, I'll just leave it alone. I'll just go, it's minus 2. Now I go to the point above it, okay, which is, and I really shouldn't have highlighted u. He's the intermediate, but okay. It's going to be this guy and this guy. What's the slope there? So 0.1 according to the differential equation, 1.98. and you get something there. Then you go, okay, so this is where I started storing stuff. I started doing stuff like, oh, this is making me crazy. So I'll just store this guy and call it A in the calculator storage. Okay. Then I went after U1, and I went, okay, I went after U2, and it becomes the old point, 1.98 this time, plus 0.1, and then times whatever that slope was. And I ended up going, well, I'm going to store that in B. Okay. And I'll show you the table in just a moment. We'll be done with this thing. Okay. And then I went for the next slope, which is equal to -2. Now this is going to occur at x2, x2, yeah, 0.2. And then whatever I got, this is where I started just going, whatever I got for B, okay? And then finally, I get to Y, and my formula looked like this, and you'll see it in the table. It looked like this. I just went Y2 is equal to Y1, which is 1.98. And then I took these two guys, and I just called it 0.05 times. And in the parentheses, all I did was A plus C. Yeah, I forgot to say this, I stored it into C. So I have ABC, and whatever this turned out to be, I stored it in D. I'm not kidding, man. I'm not kidding. But it helped me to keep it straight as to who was what so that my calculations were working. Now that's a mess. That's how I did it. And this is the table right here. Okay. Above, you can freeze it and look at the formula. This is what I used on this particular example. You do another problem, you know what changes are the slope. The formula for your slope is going to change on you. Okay. So whatever that is, but this, I hope, is helping you to do this. And if you compare, so I want to end this thing, if you compare what we got for this approximation all the way at the end, and I'm telling you, I had to be very patient on this thing right here, but I finally got there, and I think I did it right by checking it online. And then finally, if you compare that to the actual value in the previous table, look at 1.5576, and down here, 1.5575. So we're way better than the original Euler method. And so, yeah, it's worth the improvement. The next section is named after a couple German guys, Runge and Kotte. I don't speak German, but those guys have a much better way of doing things. It's pretty messy. I just have a memory of it. I've honestly never taught it before. I see it and people don't bother. But I took Mike's advice, and Mike Nassab, and we're going to take a peek at that next video. It's the third and final way of approximating these things. This has been a long video. I hope it's helpful. This is what I do, and it's how I would nail these guys down from now on. So, okay, that's it. Happy computing.